Our universe began about 13.8 billion years ago, a time so distant that it's almost impossible to comprehend. It wasn't an explosion in space, as some might imagine, with debris flying outward from a central point. Instead, it was the expansion of space itself from an extremely hot, dense state called the Big Bang, a term that can be misleading. Imagine the entire universe compressed into a point smaller than an atom, a singularity where all the matter and energy were concentrated. Then, in a fraction of a second, it rapidly expanded and cooled, setting the stage for everything we see today, from the smallest particles to the largest galaxies. The Big Bang Theory is supported by a wealth of evidence gathered over decades of meticulous observation and research. This includes the observed redshift of distant galaxies, which shows that they are moving away from us, indicating that the universe is expanding. The cosmic microwave background radiation, a faint glow left over from the early universe, provides a snapshot of the universe when it was just 380,000 years old. And the abundance of light elements, such as hydrogen and helium, matches the predictions made by the Big Bang nucleosynthesis. These observations tell us that the universe was once much hotter and denser than it is today, a seething cauldron of energy and particles, and that it has been expanding and cooling ever since, a process that continues to shape the cosmos. This expansion is still happening today, with galaxies moving apart from each other at an accelerating rate. And it's not just the galaxies that are moving apart. The very fabric of space itself is stretching. The space between the galaxies is also expanding, carrying the galaxies along with it, like raisins in a rising loaf of bread. This means that the universe has no center and no edge, at least not in the way we usually think of them. It's an ever-expanding frontier with no boundaries. The Big Bang Theory is the best explanation we have for the origin and evolution of the universe, a framework that has withstood rigorous testing and scrutiny. It's a remarkable testament to the power of science to probe the deepest mysteries of our existence, revealing a universe that is both awe-inspiring and humbling. Through the use of advanced telescopes and space observatories, scientists continue to uncover new details about the universe's early moments. Computer simulations and cosmological models help us visualize and understand the complex processes that occurred in those first few moments. We also learn about the mysterious components of our universe, such as dark matter and dark energy, which play crucial roles in its evolution. As we look to the future, we continue to refine our theories and predictions about how the universe will evolve, driven by the same curiosity that led to the Big Bang Theory. This quest for knowledge is a global effort, with scientists from around the world collaborating to piece together the story of our universe. And as we gaze up at the night sky, we are reminded of the incredible journey that began with a single, explosive event, leading to the vast and wondrous cosmos we see today. Our understanding of the universe's explosive beginning continues to evolve, but one thing remains clear. The story of the Big Bang is a testament to human curiosity and the relentless pursuit of knowledge. After the Big Bang, the universe continued to expand and cool. This monumental event set the stage for everything we see in the cosmos today. The initial explosion was so powerful that it sent matter and energy hurtling through space, creating the very fabric of the universe. Over millions of years, gravity caused matter to clump together, forming the first stars and galaxies. These early structures were the building blocks of the universe, gradually evolving into the complex and diverse galaxies we observe now. The process was slow and intricate, with gravity acting as the sculptor of the cosmos. These galaxies are not stationary. They are moving through space, often influenced by the gravitational pull of other galaxies. This cosmic dance is a delicate balance of forces, with galaxies sometimes merging or passing by each other in a gravitational ballet that can last billions of years. For a long time, scientists assumed that this expansion would eventually slow down. The prevailing thought was that the gravitational forces between galaxies would act as a brake, gradually pulling them back together. This idea was rooted in our understanding of gravity as a force that attracts and binds. The gravitational attraction between galaxies should act as a brake, pulling them back together. This concept was widely accepted and formed the basis of many cosmological models. It seemed logical that the universe, having expanded from a single point, would eventually slow its expansion and perhaps even contract. This was the prevailing view until the late 1990s, when a groundbreaking discovery revolutionized our understanding of the cosmos. Scientists were stunned when new data began to challenge this long-held belief, suggesting that something entirely different was happening. Astronomers studying distant supernovae, the explosive deaths of stars, noticed something unexpected. These stellar explosions serve as cosmic mile markers, helping scientists measure vast distances in the universe. The data they provided was both surprising and perplexing. These supernovae were fainter than they should have been, suggesting they were farther away than predicted. This discrepancy indicated that the universe was expanding faster than previously thought. The implications of this finding were profound, challenging the very foundations of cosmology. The only explanation was that the expansion of the universe was not slowing down, but accelerating. This revelation turned the scientific community on its head, forcing researchers to rethink their models and theories about the universe's fate. This discovery sent shockwaves through the scientific community. It was a paradigm shift that required a complete reevaluation of our understanding of the cosmos. Scientists around the world began to investigate this phenomenon, seeking to understand the forces driving this accelerated expansion. It challenged our fundamental understanding of gravity and the universe's evolution. Theories and equations that had stood the test of time were now being questioned, and new ideas were emerging to explain this unexpected acceleration. Something else, something unknown, was driving this accelerated expansion. This mysterious force, now known as dark energy, remains one of the greatest enigmas in modern astrophysics. Its discovery has opened up new avenues of research and has fundamentally changed our view of the universe. The late 1990s marked a turning point in our understanding of the universe. Two independent teams of astronomers studying distant supernovae made a startling discovery. These supernovae, used as cosmic distance markers, were fainter than expected. This faintness implied they were farther away than their redshift indicated. This finding was completely counterintuitive. The prevailing belief was that the expansion of the universe should be slowing down due to gravity. Instead, these observations suggested the opposite. The expansion was speeding up. This discovery sent ripples through the scientific community, challenging our understanding of gravity and the universe's evolution. It became clear that a significant piece of the cosmic puzzle was missing. Section 4. The enigmatic force, unveiling dark energy. To explain the universe's accelerating expansion, scientists introduced the concept of dark energy. This term was coined to describe a force that seems to be driving galaxies apart at an ever-increasing speed, defying the gravitational pull that should be slowing them down. This mysterious force acts in opposition to gravity, pushing everything in the universe apart at an ever-increasing rate. It's as if the universe is being stretched by an invisible hand, causing galaxies to drift away from each other faster and faster. Imagine an invisible energy inherent to the fabric of space itself, constantly pushing outward. This energy is not something we can see or touch, but its effects are profound and far-reaching. While we can observe the effects of dark energy, its true nature remains elusive. Scientists have proposed various theories, but none have been definitively proven. It's a cosmic puzzle that continues to baffle even the brightest minds. It doesn't interact with light or matter in the same way as familiar forces like gravity or electromagnetism. This makes it incredibly challenging to detect and study directly. Unlike dark matter, which can be inferred through its gravitational effects, dark energy remains hidden in the shadows. This makes it incredibly challenging to detect and study directly. Researchers rely on indirect observations, such as the way light from distant galaxies is stretched and redshifted to infer its presence. Despite its mysterious nature, dark energy is thought to make up a significant portion of the universe's total energy budget. It's a dominant force that shapes the cosmos on the grandest scales. Current estimates suggest it accounts for about 68% of the universe's total energy density. This means that the vast majority of the universe's energy is in a form we barely understand. while dark matter makes up about 27%. Dark matter, like dark energy, is invisible and mysterious, but it interacts with gravity, helping to hold galaxies together. And normal matter, the stuff we can see and interact with, only makes up about 5%. This includes everything from stars and planets to the atoms in our bodies. It's a humbling reminder of how much we have yet to learn about the universe we inhabit. Section 5. Dark Energy Theories, Exploring the Unknown. The discovery of dark energy has opened up a Pandora's box of questions about the universe's fundamental nature. Scientists have proposed numerous theories to explain this enigmatic force, each with its own implications for the fate of the cosmos. One prominent theory suggests that dark energy is a cosmological constant, a property inherent to space itself. This constant energy density would provide a constant outward pressure, driving the accelerated expansion. Another theory proposes that our understanding of gravity is incomplete, and a modified theory of gravity could account for the observed acceleration. Other theories explore more exotic possibilities, such as quintessence, a dynamic, evolving energy field that permeates space. Quintessence models allow for the strength of dark energy to change over time, potentially leading to different outcomes for the universe's evolution.